Welcome back. This is the second set of notes for circuits on current and resistance. So current is the next of our three main variables in a circuit. One is voltage, which we talked about last time. The second is current. And the third is resistance. So we'll talk about all three of these. We talked about voltage. We will talk about current and resistance today. So the definition of current, denoted by the variable I or the symbol I, capital I. I was chosen, to my knowledge, just because it was available to be chosen. You might think that because voltage is the letter V, you might think that current would be C, but current, or the letter C, is actually taken up by coulombs, or it stands for charge. So they chose I. So the definition of current is the rate at which charge flows through a point in the circuit. So I think we can just get right into the units of this, and that will make things a little bit clearer. So the units of current is called amperes, and that is just the name of them, shortened to amps a lot of the time. Almost all the time, amps. And what it is a rate of flow of charge. So a rate is always going to be over some kind of unit of time. Let's call it seconds. And charge, the unit of charge, is coulombs. So this is a charge over a unit of time. And it is not a velocity. Current is not a velocity. Like you might think it's the rate of flow of charge, or the electrons. It is not actually that. It's not a velocity. It is just a rate of flow through a given point. So if I have a wire here, and here's my point of interest right here through this loop, all the electrons are kind of whizzing past, or they're actually moving kind of slowly, but lots of electrons are moving through, but my point of reference is not moving. I'm just measuring the amount of charge going through in a given amount of time. So it's not a velocity. There are two current rules, just like voltage, for series and parallel circuits. So again, I have a series circuit. The series current rule if I have a series circuit here, and now I have currents across the battery and across each of the bulbs, because we're looking at current. And for series, the current across the battery, you would have found this in the 04 lab as well, is equal to the currents across each of the bulbs, and everything is equal here. So it's kind of the opposite. For voltage in series, all the voltage is added up to be the voltage across the battery. In current, or for current in series, everything is parallel circuits, and this is the parallel current rule. There is still a current across the battery and a current across each bulb. And for parallel, you may have guessed, the currents add up to the current across the battery. Okay, and this should have been extended as well, because I can have as many bulbs as I want. As long as they're all connected in series, that's going to be true. Same thing with parallel, this will be true. Another good thing to point out here is that in a parallel circuit, for example, we have something called a junction, which is right here, where there tends to be a split in path. We have some current going through this loop, and then some of that current continues on to go through the other bulb. And another quick rule here about junctions is that if I have a wire that splits into two or more directions, the current in is equal to the current that is going out of this junction. So let's use some real numbers. I have a current going in of 5 amps, or 5A. I would know that I would have to have any combination to get to 5, but for example, that could be 1 amp this way and 4 amps this way. But the amount of current that goes in is the amount of current that comes out of the junction. This being the junction here, the junction point. I could also flip the directions of these, or we could just do this again with some different numbers. I could have 2 amps coming in here, and then, 6 amps coming in from the other side, and then coming out would be 8 amps to the left. Now let's move on to resistance. Okay. So resistance has the abbreviation letter of R, and I guess maybe I should have mentioned up here, right? The units is amps. So this was abbreviated. I just kind of was doing it as 8A, or A for amps. The unit abbreviation for resistance is this capital omega. It's a Greek letter that stands for ohms, and which is the units of resistance. And there isn't really a breakdown for this like there was before, where we had coulombs and per second and stuff like that. It's just ohms, and resistance can depend on a few things, and that's why that unit is a little bit ambiguous. But resistance, the definition of resistance in a circuit is a property of a circuit component that resists or restricts the flow of charge. In a circuit, we've been drawing a lot of wires like this as those straight lines, or just lines in general. We tend to assume that wires have zero resistance. And we've already talked about the units of resistance. How we draw a resistor, which is a common circuit component. In a circuit diagram, we would draw this here if I had my battery. And before, we've been working with light bulbs. Now if I have a resistor, it's just going to look something like that. It's this sort of jagged line. And this signifies a resistor. And then you'll see most of the time there's something like R equals 100 ohms or something. And that would be your resistor. There's a couple rules for finding something called the equivalent, excuse me, the equivalent resistance in a circuit. Equivalent resistance, which is if I had a very complex circuit with lots of stuff going on, a resistor, and then a resistor here, a resistor there, something like that, and then we have something here. There's a lot of stuff going on. These are all resistors, or R1, 2, 3, R4, R5. An equivalent resistance is sort of calculating, okay, if I simplified all this down to just having one resistor, how much resistance would that resistor have? And this would be R equivalent, or REQ. This will probably take a couple steps for you to calculate if you need to. R equivalent for series, components in series, so that would be like R2 and R3 I could do this for. It's just the sum of the resistances. It's not too bad. So in this case, we're talking about R2 plus R3. And then let me just get rid of this just to make this a little bit easier. The equivalent resistance for parallel components, which would be, so now I've simplified this a little bit. I still have R1 here. But now I've combined R2 and R3, so I have some kind of resistor that is R2, 3, which would be R2 plus R3. Now I have two components in parallel. So to get the equivalent resistance of that, I'm going to rewrite this maybe 1 over the equivalent resistance, which this is what we want to find, is equal to 1 over R1 plus 1 over R, in this case it'd be 2 comma 3. So there's a little bit of work that needs to be done. Just to finish this off, the way you would solve for REQ is that, which gets you the equivalent resistance for a parallel circuit is equal to 1 over R1 plus 1 over R2, 3. So this raising to the negative 1 power is the inverse, or it's just, it flips your sort of fraction there. So to do that, to get my total equivalent resistance, Q here is equal to, I had to do 2 steps, right? The first step was combining R2 and R3, and then combining R1 with our R23 is just 1 over R1 plus, I mean, I wrote it over here, but R2 plus R3 is really what we did there. This was our first step. And then this is our second step. And then in doing this, and why are we doing this? An equivalent resistance will help you find the voltage across the battery, if you don't know it, or a missing current across a battery. This is a nice series circuit, so if you know the resistance in one of these, you can figure that out. And yeah, so next we're going to be talking about how all 3 of our main circuit variables, voltage, current, and resistance, relate to each other. And I guess I got into it a little bit here at the end, being able to solve for some missing values, which can prove useful in some situations.